Okay, so guys, I'm starting the lecture today. So if you find difficulty in hearing my voice or if I'm not audible, please let me know first. Okay. So good evening to all of you. Today we are going to discuss about Introductory Organic Chemistry Part 2, which is a NPTEL platform course, and the course instructors are Professor Harinath Chakripani and Professor Neeraja Dashaputre from ISER Pune. So I am Simran, your PMRF teaching assistant. So guys, today's topic is, as you guys have known that I have already taken this particular course previously as well. So there are videos on my channel which is present. So you can go through that videos. And today we are discussing about the week 1 topic, that is NMR and aromatic substitution. So NMR, we are mainly concerning about the proton NMR and the carbon NMR, that is 1H and 13C NMRs. So we are going to look about the questions today about 1H NMR, 13C and aromatic substitution. So I'm starting from problem number 1, that is, you have to identify the number of distinct signals in the 1H NMR spectrum. So now this is the compound in your screen, and you have to tell me that how many signals would be there for this compound in 1H NMR. So first of all, you need to know how many different type of hydrogen is present in this particular organic compound, right? So for knowing that, you have to know how many CHs are there, how many methyl groups are there, how many CH2s are there. So can anyone tell me how many CH2s are there? Try not to type, just unmute yourself and tell me. So how many CH2s are there?
One.
1. So this is 1 CH2 that is present here. How many CHs? 4. Right? These are the 4 aromatic CH which is present. And how many CH? This is another CH which is present here, right? So apart from this aromatic CH, you have another aliphatic CH which is present here, and these are the two methyl groups, right? So these are two methyl groups. So guys, you have to answer me that how many number of distinct signal could be present for this compound. So as you can see here, this compound, is it symmetrical? Can anyone tell me, is it symmetrical?
Yes.
Yes. Okay. So if you are telling me that it is symmetrical, then these 4 hydrogen should show similar chemical shift values. So is it so? Can these 4 hydrogens are showing similar chemical shift value? Are these 4 hydrogen identical?
No.
No. Because these 4 hydrogens are facing different environments. That is why these 4 hydrogens are not at all identical. So what is happening here? See, these two protons that is present on this side is facing what? This CH2 and bromine. So due to the de-shielding effect of this Br, the electron density it will take away and it will become more downfield. Right? These protons will become more downfield. Due to the presence of electronegative atom, that is bromine here in our case, these CHs show different environment from these CH, because now as you can look at here, these two protons, what is the adjacent group which is present? These two methyl and this CH. So this methyl group doesn't impart that much shielding or de-shielding effect on this particular system, and that is why you will find that these two proton which is closer to this bromine will show you a higher chemical shift value rather than these two protons. So now we come to a conclusion that these 4 protons are not identical, right? So now if it is not identical, then these two proton which is present in the same environment will show chemical shift similar and will show a one signal in particular 1 HNMR, right? And similar for this case, these two protons, as the environment for these two protons are similar, that is both are facing towards the methyl group. So that is why they are showing a chemical shift value that is identical, right? So because of these two, one signal should be there in 1 HNMR. So because of these two, four hydrogens on the aromatic side, you will find two signals in 1 HNMR, right? So this much is sorted. So now you have to think about this CH2, these two CH3, and this CH. So now coming to this particular CH2 group, just tell me that these CH2, will it show chemical shift value similar or different? See, I'm talking about these CH2s. So these CH2s are identical in nature because there is no chiral center that is present on the adjacent point. If there is a chiral center that is present on this side or this side, then you will see an anisotropic protons that are present on this carbon, and you will then see that these two protons will give you different signals in 1 HNMR. But in our case, luckily, here there is no chiral center which is present adjacent to this particular CH2. That is why these two CHs are now identical. So you will see one signal for these two protons in 1 HNMR, right? So now this much is sorted. Now you have to worry about this particular group. So there are two methyls and one CH. So can anyone tell me, is these two methyl different or similar? Like they are identical
Similar.
or not? Yeah. So they are similar. Why? Because now these two methyl groups are facing similar environment. That is why these two methyl will show a sharp singlet in your NMR. So here you will find a one signal for these two methyl groups. So these protons are sorted of aromatic ring. So till now you have four signals in the 1 HNMR. So now we are left with this CH only. So this CH will show you another signal because it is now not the aromatic CH, it is the aliphatic CH. So that is why apart from the CH which we have seen in the compound that are aromatic, this aliphatic CH will give you another signal in the 1 HNMR that is different from this aromatic CH. So this will show you one another signal in 1 HNMR. So here we can conclude that these two CH2 will show you one signal, these orthoprotons will show you one signal. These two again the aromatic CH protons at the ortho will show you again one signal for this CH and one signal for these methyl groups. So how many total signals do you see in 1 HNMR spectrum? Can anyone tell me now?
I
Five. So you will see five corresponding signals for this particular compound. So is it clear, guys? Anything which is not clear? So I am assuming that it is clear to all of you and I am moving forward. So now coming to the problem number 2. Now problem number 2 is also a similar kind of question. Now they are asking which of hydrogens from A to D in the following molecule give you a triplet signal in the 1 HNMR spectrum. So now you have to answer that amongst these A, B, C and D protons, which proton can give you a triplet signal in the 1 HNMR. So now one more
see.
C, yeah. But I am actually asking from the whole class. So guys, if you don't know, then let me tell you what is this. So C is the correct answer, but why C is giving you the triplet signal, we have to see here, right? So now among this A, B, C, D, so first of all we will go to A. So this methyl. So signal or splitting in the 1H NMR is because of the neighboring protons that are present on the particular carbon, right? So here you can see that in the case of methyl, that is Ha protons, there is no adjacent group which is containing the protons. There is a carbonyl group, but here there is no proton that would split this particular signal into a further signal, right? So that is why here you will see a sharp singlet for this methyl group. Coming to Hb protons, what will happen in this case? Now this hydrogen have a vicinal hydrogen present. So now this Hb will show the splitting because of Hc carbons. So because of the Hc carbons, what will happen? So this is Hb protons, right? So now because of the Hc protons which is present here, it will show a splitting. Because one proton is present in the adjacent, so now the splitting will be a doublet. Why? Because as we have came across that there is a rule that is 2Ni plus 1, but for the proton the 2Ni value, that is the I value for the magnetic moment, is half. So if you are saying that this is 2Ni plus 1, which is the splitting rule, I for the proton is half, right? So that is why if you put the value of half, this 2 will cancel out and you will left up with this n plus 1 rule. So now we are calling it as n plus 1 rule. So according to the n plus 1 rule, what will happen that n is the neighboring proton that is present, that is responsible for the splitting. So now in our case, Hc has only one proton. So n is equal to 1. So equal to 1, then we will give a value of 2. So here the signal of Hb protons will further be splitted to a doublet because of the Hc proton. So these will show you a doublet, right? So now coming to Hc proton now. Hc proton will also show a splitting because of the Hb proton that is present here. See, they will also show a splitting pattern if there is a proton which is present on the another side. But as you can see here, there is a oxygen which is attached to the CH, right? Due to which it will not split this particular CH up. So the splitting is because of the Hb only. So Hb now have two protons. So the n value is now 2. So 2 plus 1 is equal to 3. So that is why now you will see triplet for the Hc protons. So now because of the Hb proton that is present at the adjacent carbon, you will see a triplet for Hc protons. And again these methyl will show you a singlet because there is no neighboring protons that are present because of the presence of oxygen atoms. So they again will show you a singlet. So now the Hc proton is the proton which will give you a triplet signal only in the organic molecule, because everyone here is showing a singlet, a doublet, triplet and singlet again for this particular methyl group. So here we will see that a triplet signal for Hc protons is because of the splitting by the Hb protons. So the correct answer will be the hydrogen C will give you the triplet signal in 1H NMR. So I hope it is clear to all of you. If you have any doubt, please ask me guys right now. If you have any doubt, any problem regarding this question. Okay, if there are no doubts, I am assuming that you guys have got the answer. So coming to problem number 3. So now the problem number 3. So they are asking the number of peaks possible in proton NMR for the following compound. So again you have to identify the how many protons that are present, how many different protons that are present in the compound to show you different signal in the proton NMR. So now there are 4 protons that are present, right? So these 4 protons. So is the molecule symmetrical or not?
Symmetrical.
Yeah. So you can see that this is the symmetrical molecule. So if it is symmetrical, if we pass a plane then it will cut the molecule into two equal halves. So now if the compound is symmetrical, then these two protons are the mirror images of these two, right? So that is why these four protons are equivalent in nature. Because of the presence of this oxygen, this is although getting deshielded, these four protons is getting deshielded, but what will happen if you are asking about the number of peaks possible, then you have to see how many different protons that are present in the compound to give you the different signals. But now in our case, all the protons which are corresponding for the proton NMR are equivalent in nature. So now if they are identical, they are equivalent, then they will show only a single peak in the 1H NMR. So now these four protons will give you one signal for the 1H NMR because of the identical nature, right? So is it clear to all of you why they are showing only one peak? Okay, assuming that you guys have got the answer, so this particular compound will show only one peak that is possible in proton NMR. So the correct answer will be option number C, right? Okay, guys, please,
Yes.
yes, please respond so that I can know that you guys are here only. So, coming to problem number 4 now. So now it is about 13C NMR, not the 1H NMR, but it is about the 13C NMR. So here they are asking that the 13C NMR signals are in the following order of chemical shift. Now A, B, and C, you have to identify the chemical shift value for these three protons and you have to arrange it in the order, either increasing or decreasing according to the options. You have to identify the trend of the chemical shift. So here coming to A part, here they are asking about the methyl that is attached to the carbonyl group. In the B, they are talking about this carbonyl group chemical shift value. And in the C, they are talking about the aliphatic aliphatic CH3 groups. So can anyone tell me among these three which will be having the highest chemical shift? Is it A, B, or C? The higher chemical shift value in the 13C NMR. Is it the carbonyl group?
B, B is more B shielded.
Yeah. B will be highly shielded or deshielded. So it is having a higher chemical shift value in the 13C NMR. So coming to some of the values of 13C NMR. So guys, you can see here the chemical shift is ranging from 200 and 220 for the carbonyl group. So maximum chemical shift for the carbonyl group is ketone carbonyl group is showing the maximum chemical shift value in 13C NMR that is ranging between 200 to 220. After that, aldehyde will show up at 190 to 200, and after that acid, and then you will see the peak for ester. So this is what the trend of the 13C NMR. So why is it so? So here you have to answer according to what? The polarization. So as we have seen here, this RR is methyl or methyl in the case of ketone. So now they are showing the higher deshielded values. Why? Because there is a higher polarization at this carbonyl group. Because of the push-pull effect of this CH3s, there is a polarization that is corresponding to give you a C plus partial positive charge with a O minus. So here the partial positive charge is coming on this carbon and oxygen. That is why it is getting highly polarized. Due to the polarizability, because of the presence of these two methyl groups on both of the side, the carbonyl group strength is getting weak. So now the bond length is getting increased. So if the bond length is getting increased between this carbonyl, then you will see a deshielded chemical shift for this particular compound. So here also you can see that one of the methyl group is now replaced by hydrogen. So here the electron density at this carbon, the electron density is very much high because of the presence of these two methyl group, right? But as you can see, one of the methyl is now replaced by hydrogen. That is why the carbonyl electron density is getting lower. So that is why there is no much polarization that is present as compared to the ketone. So that is why you will see a lower value of chemical shift for the aldehyde, right? So that so here the polarization and the chemical shift values, the bond length strength depends which will get a higher deshielded value and which will get a lower deshielded value. So you have to be very careful according to the carbonyl groups. There is a trend which you have to follow that ketone will show up at 200 to 220 chemical shift value in the 13 cNMR because of the higher polarization, right? So there are some values you can look into this table. And now we are coming back to the question that is here. The chemical shift values for this B will be the highest because here also we have a ketone that is present. So it is also ranging among like 200 to 220, and or otherwise because of the delocalization here, it can also get reduced from 220 but not much more than. Okay. So now carbonyl group is having the highest chemical shift. Now just tell me among this A and C, this methyl that is present at the alpha position of this carbonyl and the methyl which is present at this acyclic position, which will be having a higher chemical shift value? Is it the A or is it the B?
A.
A. Because of the presence of this carbonyl here, this methyl group is become de-shielded than than this methyl which is present at this position. So now this A will be having a higher chemical shift value than the C. Here you can see that similar to this methyl which is present at this ketone, we are getting a higher chemical shift value, and acyclic methyl groups, that is this, is ranging between 0 to 35. So guys, here we can see that this will range from 0 to 35, but here because of the presence of alpha carbonyl group, the chemical shift for this methyl will go up. So that is why the trend will be the B will be having a higher chemical shift value than A and then C. So this is how we are arranging the chemical shift value in the order. So now tell me which will be the correct option for this question.
B option.
Option number B. Yeah. So option number B will be the right one. So I hope this question is clear to all of you. And for this particular kind of problems of chemical shift values, you have to go through the table and you have to actually remember some of the values, and you have to actually remember the concept behind the values so that it will be easy for you guys to understand, right? So now I hope it is clear to all of you. Problem number 4.
Ma'am, in aldehyde versus ketone, don't we consider plus I effect of two methyl groups in ketone?
Actually, there are multiple effects which is playing in this condition. Okay, so the push pull effect of these methyl group is also playing a role, and also the minus I effect is playing the role here. But what happened? The minus I is not that much because methyl groups are not playing that much effect for in the minus I, right? So here the electron density is not that much taken away by the methyl group, because as you can see in the acid chloride means like you have this Cl group here, right? And this carbon. So here you can say that yes, minus I effect is playing a role because of the Cl group. Here it will actually screen out very much electron density at this carbonyl carbon. So here it will become more uh, like electron deficient than this ketone. So that is why I'm saying that here if you are considering Cl like halogen atoms or the nitro groups, they are giving you much more higher minus I effect than the methyl groups. So methyl groups are not that much strong minus I effect containing groups, right? So that is why
Yes.
here you will see that push pull effect will be more like more operative here than the minus I effect.
Yeah, but the carbon delta positive will be more stabilized by two methyl groups, whereas aldehyde only has one proton, hydrogen in R group.
Mhm, yes. So what I
Yeah,
mean
so
by,
that I was thinking.
yeah, yeah. So the chemical shift is actually based on the electron density increasing or decreasing at the carbonyl carbon center. So that is only the concept is,
Okay, okay.
right. So just take a look, just go through the things, like you can also see about you can also see between the ester, amides, acid chlorides. So the trend is there, so you can see that trend, and you can actually like see which factor is much more operated in when in what case, right. So in this acid chloride case, the minus I effect is very much operative there, but in these case the push pull effect is very much there. Okay, so I hope it is clear now.
Yes, ma'am.
Okay, so coming to problem number 5. So problem number 5 is stating that you have to tell that if the more shielding effect is there, then what will change? Like, what is meant by the shielding effect was, first you have to know what is the shielding effect, right? So for that, here there is a picturization, guys. So here what will happen, that when your nucleus will resonate with the electromagnetic field which you have applied. See, when there is an electron and you have applied a magnetic field, the particular nuclei will resonate with the applied magnetic field. But now if the nuclei having the electron density around it, now the electron density will again generate a induced magnetic field, that is this. So this induced magnetic field is generated by the electron density that is surrounding the nucleus. So which will now oppose the magnetic field which you have applied. So now the shielding is this. Once your nucleus is resonating with the applied magnetic field and the generation of this induced magnetic field takes place, so the shielding of this induced magnetic field from the applied magnetic field. So here your nucleus is now surfaced by the induced magnetic field from the applied magnetic field. So here, if you have applied like 500 megahertz of the applied magnetic field, just say that you have applied this 500 megahertz. So now your nucleus will not feel the 500 megahertz. What it will feel, that how much secondary induced interactions are there, so it will minus this particular applied magnetic field, so it cut down the intensity with which you have applied the magnetic field. But it will feel what the magnetic field is now is equal to the magnetic field of the applied magnetic field which you have applied already, right, and minus the induced magnetic field which is getting generated due to the electron density surrounded by the nucleus. So now this is the net magnetic field which is experienced by your nucleus. So higher is the shielding effect. So what will happen now? The question is asking, if the shielding effect, that is the secondary interactions, are higher enough, then what will happen? So coming back to the question, if the secondary interaction, that is the shielding, is higher enough, then what will happen? It will lower the chemical shift. There is no change in the chemical shift. Higher the chemical shift or more the peak splitting. So now you have to take these things of shielding in the mind, and you have to answer whether the chemical shift of that particular nuclei which is now resonating with the electromagnetic field which you have applied, is the chemical shift is getting lower for the particular nuclei, is it the getting higher, is there is no change, or the peak splitting is observed. So now you have to tell accordingly. So now just tell me, if the induced magnetic field is higher, then what will happen? So the magnetic field which your nucleus is now experiencing is less than the applied magnetic field, right? So now the magnetic field which the nuclei which my nuclei is experiencing is less than the applied magnetic field, right? So if it is less, then it will resonate very quickly. So lesser is the lesser is the net value of the magnetic field, more quickly it will resonate with the resonance frequency. So now there is a very important concept here. If your shielding effect, the induced magnetic field which is generated around the nucleus is very high in magnitude, then your applied magnetic field will cut down onto that much of the amount which is present in the induced magnetic field. So now the magnetic field which your nucleus experience is lesser than the applied magnetic field, and now it will change the frequency. So now your nuclei will resonate with the applied magnetic field very quickly than the previous one. So is this much clear to all of you, or there are any doubts, anything which is not clear? I'm just talking about this concept. Any answers, guys? So is it clear or
Yes, ma'am, clear.
okay, okay. So if you are getting this concept, then what will happen now? In coming back to the question, now they are asking you if the shielding effect, that is the secondary interaction that is coming from the electron density around the nuclei. If the shielding effect is higher, then what will happen? Your nuclei will feel the lesser amount of resonance magnetic field which is present at the applied magnetic field. So now your nuclei will tune, or your nuclei will resonate with the frequency very quickly. So here, if the shielding effect is high, what will change? Can anyone tell me, based on that particular experiment only?
Lower the chemical shift.
Lower the chemical shift. So here, what is happening, that the induced magnetic field is getting increased and now the net magnetic field is getting down. So lower the net magnetic field, and lower is the chemical shift value, because now your nuclei will resonate very fast with the magnetic field. So this is how you can say that if the shielding effect is high, your chemical shift value will be lower. Is it clear, guys?
Yes.
Okay. So now coming to problem number 6. So it is different from the NMR. So we are not dealing with the NMR questions here. So what is question is asking, for the following reaction scheme, identify the reagents. Only you have to do is the identify A and B. So here there is a normal Friedel-Crafts reaction which is happening on this benzene ring, right? So now you have to identify which of these particular reagents is applicable for this transformation to take place. As you can see, B is common for all the question options. So B is common.
Third option.
Third option. Okay. So anyone else having any other answer rather than C? See what will happen here. So here the mechanism which is there is, now you have to have this particular ring at this position. So this is the Friedel-Crafts acylation. So here what happens, this aluminum chloride which you have added now takes up this Cl and form a salt, that is a tetra complex which is forming with the aluminum. So here this acyl cation is getting generated, and now this acyl cation is getting trapped by the benzene ring. So benzene ring is electron rich ring, that is why it is getting attacked onto this acyl cation, and you will have this alpha positive charge generated at this carbon. So this positive charge is now getting again aromatized, and you will get this particular compound. In case A, what you will have is COCH2CH3, and here also you will have this, but now they are acting a Lewis acid in this particular situation where they have not added this AlCl3 that is playing as a Lewis acid. So if Lewis acid is not there, this activation is not there. So if this activation is not there, then acyl cation is not going to generate. So which is now is not getting trapped by the benzene ring. So that is why the option A is wrong, although it is containing the correct acyl chloride, right? So in option second also, the A is not having any of the Lewis acid, which will make this particular compound a acyl or a cation can get generated. So in the case of C and D only, they have added the Lewis acid. So if we consider the D part, then what will happen? Now you will generate a acyl cation here, but only containing a methyl group. So what you will get, this CH2 part you will not get, and you will get a CH3CO which is trapped by the benzene ring, and you will get a particular compound. But here one carbon is needed, and that is why the option number C will provide you that another carbon. So after having this electrophilic substitution reaction, now they have added the in the same pot they have added zinc amalgam in HCl. So it is nothing but a Clemmensen reduction. So where this carbon will get reduced to give you this alkane. So this side chain is getting reduced to give you this particular compound. So the correct option will be option number C. So is it clear to all of you why these A and B are not the correct options?
Yes, ma'am.
Okay. Okay. So if it is clear, then going to the next problem, that is problem number 7. So in problem number 7, they are asking again one NMR question. So they are asking how many.
Two.
Okay, guys, please just let me read out the question and then you will answer it. I know you people are smart enough, but still, I have to do this. So coming to the question, how many number of peaks are possible in 1H-NMR spectra of the following compound? So this compound is ethyl chloride. So again they are asking the number of possible peaks. So now you have to identify how many different protons present in the particular system. So this is the expanded version. So here how many different protons are there? You can see this methyl group and the methylene group. So here these three protons of methyl are equivalent. So these are having the similar environment. So that is why we can say that yes, they are equivalent in nature because of the same environment that is present. So that is why they will give you a single peak in the 1H NMR. So you will see a one peak for this particular methyl group. So now coming to this methylene group, here also these two protons are having similar environment as it is attached to one of the chlorine and one of the carbon containing three hydrogens. So similar environment is present for this ethylene. That is why these protons are also equivalent. So you will see one another particular peak because of this methylene group. So in total you will see one peak for this methyl and one peak for this methylene. So total two peaks are possible in 1H NMR spectra of this compound. So the correct option will be option number B. Right? Is it clear to all of you? Okay, so
Yes.
yeah, so it is clear. Moving forward to option number 8, problem number 8. So they are asking in NMR spectrum, the nuclei in a field resonate at high frequency, low frequency, it is constant throughout the spectrum, it doesn't depend on chemical shift. So you have to identify the correct option in which the question is saying that in the NMR spectra, the nuclei which is present at a field is resonating at a high frequency or a low frequency. So guys, first of all, you need to know that what is upfield, what is downfield. So this is what the spectra looks like. So here the delta ppm value of the chemical shift. Here the shielded region that is present at this 1, 2, 3, and 4 is known as a field region, and the downfield region, that is the de-shielded region, is known as downfield region. So uh, every time we get confused that upfield means the higher chemical shift value and downfield means the uh, lower chemical shift value. But here the things are opposite. Upfield means the lower chemical shift value and downfield means the higher chemical shift value. So shielded region is having a lower chemical shift values, whereas the de-shielded region is having the higher chemical shift value. So now question is asking that the nuclei which is present at a field, nuclei is present at a field. Now they are asking whether it will resonate at lower frequency or higher frequency. So now the same concept arrives here of the shielding and de-shielding. So we have talked about previously that the shielded nuclei, the nuclei which is having higher electron density around it, will produce a higher induced magnetic field, which will cut down your applied magnetic field to a very much extent. So here also the same concept relies here. What will happen now, you will see that higher the shielding of the particular nuclei is there, higher is the probability that it will resonate at low frequency. So we have talked about there about this particular shielding effect. So now in the question it is they are asking that the nuclei again which is present at the upfield, that is the nuclei which is shielded, will resonate at a high or a low frequency. So can anyone tell me what will be the correct answer for this question?
Low frequency.
Low frequency. So now why there is low frequency? Because the shielding is there. So here the induced magnetic field will be that much high that your nuclei will tune with the frequency very much faster. So that is why they will resonate at a low chemical shift values. So is it clear to all of you? The correct option will be low frequency. B will be the correct option. So is it clear?
Yes, ma'am.
Okay. So if it is clear, then I am going to problem number 9. So just take a look to these slides also. Just be sure that you guys are getting what I am saying. All of you. I'm not talking about one or two people. So just go through these slides as well. So now in coming to the problem number 9. So problem number 9 is asking the possible number of peaks in 1H NMR spectra for this particular compound. So possible number of peaks. So how many different type of hydrogens present in this system?
2.
Two. One is this particular hydrogen, that is Ha. Another is this Hp. So why there are only two protons that are present? See what will happen here. Hydrogen that is connected to this two chlorine atoms will show you a chemical shift value very much different. And coming to this particular carbon, here these two protons having the same environment, because as you can see for H, this proton, it is also connected to 1Cl carbon atom hydrogen, and adjacently B, it is similar. Once you are getting on this particular proton, then also it is attached to a carbon connecting to a chlorine and connecting to another carbon containing chlorine and hydrogens. So that is why the connectivity and the environment for these two protons are similar, and you can say because of the similarity that you will see only two proton signal in 1H NMR. So one is because of this hydrogen Ha, and one is because of these two protons, that is Hp. So total two signals are visible in 1H NMR spectrum of this molecule. So correct option will be option number B. So is it clear to all of you, everyone? I'm just thinking that you guys are knowing this concept already because of the attentiveness in the lecture which is given by ISET Pune's course instructors. So I'm just taking up the tutorial and nothing else. So I'm assuming that you guys have already know the concept behind this, and I hope that these questions are clear, and these questions are very simple enough to understand or to start with the NMR spectroscopy. So is it clear to all of you?
Yes.
Okay. So coming to problem number 10. So they are asking which of the following solvent is not used in NMR? Is it the deuterated water, B chloroform, C carbon tetrachloride, or D CdCl3? So which is the solvent that is not used in the NMR? So can anyone tell me which is the solvent is not used in the NMR?
Chloroform.
Chloroform. Right. So chloroform is not used in the NMR in because as you can think that you have to add some standard to get the NMR spectrum done, right? So to get the NMR spectrum, you have to add with your compound a standard that will not interfere with your peaks of the of the organic compound which you are taking the NMR, right? So if the particular solvent is interfering with the peaks of your interest NMR, then the solvent is of no use, right? So here we will take deuterated solvents for recording the NMR spectroscopy rather than the normal solvent that is DCM, chloroform and all. So we are not taking that particular things because of the presence of these protons. So guys, this proton of chloroform will show up in the NMR, and that is why we are not interested in this chloroform. So we need some solvent that will no show any imprint of that particular solvent in NMR. So your NMR will contain only your peaks rather than the other peaks. So for avoiding these kind of things, we use the deuterated NMR. And also to facilitate the locking and shimming, which you guys I think has upper look only what is locking, what is shimming. So here, what will happen if this deuterated solvents are not used, then the locking, that is the standardization of the NMR will not be done properly, and also the shimming is the intensity of your peaks. So if your compound is showing some of the peaks, if there is no shimming in the spectrum, then the intensity, the quality of that NMR is getting compromised. So that is why the traditionally in everywhere we are using the deuterated solvents, because deuterium is the heavy isotope of hydrogen and it is showing the main reason for using the deuterated solvent is it never shows you the resonance frequency of the NMR. It never resonate and in the magnetic field which you have applied. If it is 500 megahertz, 400 megahertz in the NMR, the deuterium will never show up in these radio frequency. So it needs higher radio frequency to be shown in the NMR, and that is why the deuterium is the very much or lovable solvents in this particular NMR. So now deuterium will never show up in your NMR in the radio frequency which you have applied or the normal radio frequency in which NMR is recorded. So that is why the deuterated solvents are the traditional solvents which are used. So, to facilitate the locking and shimming, we traditionally use it. And now, here, if we consider the option number A, this is D2, that is the heavy water. So, it is the correct thing which we can use in this NMR, but chloroform we cannot. And tetrachloride is there is no hydrogen peak that will interfere in your NMR, right? We are not talking about the carbon NMR. I'm just talking about the proton NMR. There is no proton peak which will be interfering in your proton NMR. And CdCl3 is the most common solvent which is used in NMR. Most common solvent. It is nothing but the deuterated form of this chloroform. So now CdCl3 also contains some of the water molecules. See here, if you can see that in recording NMR in CdCl3, There is also a peak which is coming due to the CTCl3. Not very much intense, but coming because of the CTCl3. Because here sorry, proton deuterium exchange is taking place. So that is why what happens, the CHCl3 proton is going to show up in the proton NMR. But if you take the chloroform only, if you are not taking deuterated solvent, see these deuterated solvents are 98 or 99% clean, but that 1% will show up in NMRs because NMRs are very sensitive instruments, so the 1% is showing up. But if you can imagine that 100% of chloroform you are taking and recording the NMR spectrum, then it is impossible. You are only getting the chloroform peak for that particular NMR. Your organic compounds peaks are just vanished. You will only see the peak for chloroform proton, right? So that is why there is a main thing, and the main concept behind is that deuterated solvents will not show up in the proton NMR, and you will get a good quality of spectrum which you require. So that is why chloroform is not the solvent which is used in NMRs. So is it clear to everyone? So is it clear, or anyone has any doubt regarding this? Just take your time, just think about it.
Ma'am,
Yes,
what is the exact syllabus for Introductory Organic Chemistry Part 2?
I think you have enrolled in the course, right?
Yeah.
So I think you will be able to see the week one, week two, like that setup, because it is given on the channel only. It is given on the particular channel, and those people who have enrolled can get to the syllabus, uh, logging into
Because
the
they
particular.
mentioned the syllabus is alcohol, phenols, and aldehyde ketones, not
Actually,
any.
actually, you are looking at the older syllabus, I think.
Okay, so new syllabus include NMR spectroscopy.
Yeah, yeah.
Okay,
The particular, actually they shuffle the contents. The
okay,
contents are same, but the week which we are taking up that particular content, they have shuffled.
okay.
Okay.
Yeah, thank you.
So is the question clear to all of you? Should I move ahead? Can anyone respond?
Yes, ma'am, you can go.
Okay. So assuming that it is clear to all of you, I'm going to problem number 11. So problem number 11 says which is most reactive in electrophilic substitution. So now you have to tell me that which is most reactive in the electrophilic substitution reaction.
B.
A. Okay. Any other answer than A?
No, I said B.
Okay, you said
B,
B.
Yeah.
Okay. My bad. So any other answer other than B?
D,
D. D, right?
yeah.
Okay. So now they're asking which is the most reactive compound in electrophilic substitution. So what is electrophilic substitution, guys? Now first you have to look at what is electrophilic substitution. So now one electrophile is getting trapped by the electron density of the particular ring. So that is where electrophilic attack first takes place, and after the proton lows, you will have the aromatized ring again. So now, one by one, we will see what will happen. See, this is the allyl chain. So, will it increase the electron density of this benzene ring? See, benzene ring is already electron rich, but now the most reactive is the electrophilic substitution is what the species containing the more electron density, right? Because now they have to trap a electrophile. So to trapping a electrophile, the ring should be electron rich enough. So here the alkyl group is not giving any significant change in the electron density of this benzene ring to make it reactive, to make it more reactive towards the electrophilic substitution. Now coming to the part C. Similarly here, what will happen? Is it making the electron, is it making the ring electron rich or electron deficient? Part C I'm talking about. Is it making this ring electron rich or electron deficient? This particular group. Any answers? So now what will happen, guys? This carbonyl group is electron withdrawing, right? So it will withdraw electrons from this ring. And now what will happen? This ring is now becoming more electron deficient than previously. So now if you compare a benzene ring and a ring containing this carbonyl group, then which one is more electron deficient? The ring containing this carbonyl group, because of the presence of electron withdrawing group, that is this carbonyl, it will withdraw electrons from the benzene ring and it will make it less reactive towards the electrophilic substitution, because if it is not having the proper electron density present, then how it will be more reactive in the electrophilic substitution, because now this ring has to trap one electrophile, right? So for trapping that electrophile, the ring should have enough electron density. So coming to part number D. So here also the similar concept takes place. Cl is a electron withdrawing group, right? It is not a electron releasing but a electron withdrawing group. Because of the minus I effect and electronegativity of this particular chlorine, what will happen? Now it will also take up electron density towards itself, and that is why it is make it is making this particular ring electron deficient than the benzene ring. So any ring containing electron withdrawing groups on it, it is less reactive towards the electrophilic substitution. Because if you talk about the nucleophilic substitution, na, then it will be high in reactivity, because for nucleophilic substitution you will need a electrophile. So for electrophilics, then for electrophilic rings you need electron withdrawing group. So if we talked about the nucleophilic substitution, then these options are great enough. But now in our case, electrophile has to trap by this aromatic ring. So we need electron density which is higher in these benzene rings. So now tell me, among these four options, which option is connected to a electron releasing group?
A.
Electron releasing group I'm talking about amongst these four. So this A and B, guys, it is not connected to any electron withdrawing group, right? But now the electron releasing group is OCH3, that is the methoxy, because now this lone pair of oxygen is present in the conjugation, right? It is giving the electron density in this particular ring. But here, this alkyl group has nothing to do with the electron density, because it is not a releasing, not a withdrawing group. So that is why this OCH3, that is the methoxy group, is actually giving up the electron density in the aromatic ring, and that is why it is making this aromatic ring much more electron rich and much more reactive towards the electrophilic substitution. So is it clear to all of you? Now tell me, which is the most reactive species in electrophilic substitution?
Methoxy group.
Yeah, the OCH, that is the methoxy group. So the correct option will be option number B. Right, because every other option, that is C and D, is connected to electron withdrawing group. which will withdraw electron from the ring and it will make the ring less reactive towards electrophilic substitution. But in the case of A, it is neither electrophilic, neither nucleophilic. It is having the similar kind of reactivity as that of benzene ring. But now they are asking that benzene ring is also reactive in electrophilic substitution, no doubts, but they are asking which is the most reactive. So now you have to identify if a if a benzene ring contains an electron releasing group, then it will make it most reactive in the electrophilic substitution. Right? So is it clear to all of you? Any doubts?
Ma'am, don't we consider plus R effect in D?
Plus,
It could be possible.
yeah, lone pairs of chlorine, right? But
Yes.
actually, the donation ability, you can say that methoxy group has the more donating ability, because
Yes.
so that is why we can say that yes, B. They are asking in the question most reactive, right? Although it is having
Hmm.
a plus R effect, but it is also having a minus R effect. You cannot neglect the
Yes.
electronegativity of the chlorine. It is also an electronegative atom, right? So it is also having the minus
Hmm.
I. But in our methoxy case, it is having a plus R and plus I effect only. So that is why the operation of these two effects is higher in the case of B rather than the D. So if you are comparing these two both, then I can say that yes, B is most reactive than D, right?
Hmm.
Although if you
Yes.
compare D and C, then you can say yes, D is most reactive, because D is more reactive in the electrophilic substitution than C, because C is attached to a very high like electron withdrawing group, that is a carbonyl group. It is
Hmm.
although very electron withdrawing, that is why the ring is highly electron deficient in the case of C, but in the case of D, it is not that much scenario, right? It is also showing a plus R effect. So as you have said that if I compare C and D, then D is a in a much better situation than C. So electrophilic substitution is readily takes place in the case of D, but rather than the C, right? So if you compare C and D, D is good, but if you compare the whole list, B is very much reactive. Okay.
Yes.
Yeah.
But ma'am, in ipso substitution,
Hmm.
could D be more reactive than B?
But in ipso substitution, as if you have studied it, that then you know that fluorine leaving ability is higher than chlorine, bromine, and iodide, right? In that particular scenario
Mhm.
of ipso substitution, because there is the rate determining step which is present on the leaving group. So
Yes.
in that case, fluorine ability is higher. But now we are only talking about not the replacement or the displacement. We are talking about the electrophilic substitution reaction. So here, electrophile has to substitute from this benzene ring. It is not getting substituted along with this Cl, right? Now here Cl is not a leaving group. You are considering it as a leaving group, but it is not. So it will not leave out that much fast. Fluorine will leave out in the ipso substitution fast, then chlorine, and then bromine, and then iodine, right? So that is why ipso substitution is not playing any significant role in this particular case. Because we are not comparing only D, we are comparing a list of four compounds, right?
Okay. Okay.
Yeah, if you compare the halogen atoms only, chlorine, bromine, fluorine, iodine, then surely the ipso substitution will take a role there. Okay.
Okay.
Yeah.
Hmm.
So is it clear?
Yes.
Okay. So if it is clear, then I'm moving towards question number 12. So it is a very simple question, guys. So they are asking equivalent protons in a molecule will have a same environment, same chemical shift, same shielding effect, or all of the above. Just tell me quickly what is the correct answer.
All of the above.
Yeah, all of the above. Because if you can compare the molecules which have the equivalent protons, that is, if you compare this benzene ring, right? So if this benzene ring without substitution have similar kind of protons, have all the protons that are equivalent, then they will have a same chemical shift value, they will resonate at same chemical shift value, they will have a same environment, and they will also show you the same shielding effect, right? So that is why we are saying that the identical protons or the protons having the equivalent protons, they will show up on a same chemical ships, same environment they will have, and same shielding effect also they will have. So the correct answer is all of the above. So is it clear to all of you? So based on what we have said previously, what we have seen about the equivalent protons, non-equivalent protons, it is just a passing question that you can easily answer, right? So I hope it is clear to all of you. So coming to problem number 3, just go through these molecules and you will get to know that yes, they are showing up a single peak in the 1H NMR. Okay. So these are some chemical shift values which I have mentioned. So this video will be available for you to watch on my YouTube channel, so you can actually take up there your questions also. So just tell me in the comment box or just tell me in the next session. So either way you are comfortable with. Okay. So now coming to problem number 9. Is it 9? No, no. 13, right? And what happened? Okay. I added a extra question, guys. So coming to this problem, how many number of peak splitting will be observed for secondary proton in the following compound? Okay. So now there is a another scenario. They are asking you the number of peak splitting, not the number of possible peaks in 1H NMR. Okay. So they are asking you the peak splitting. How many peak splitting will be observed? So now you will play with the n plus 1 rule here. So I am coming to first of all this gamma proton. So guys, tell me how many splitted peaks will this methyl will show me because of this CH2. If this is
Three.
3, right? So if this is HA proton and this is HB proton, then I can say the HA proton is further splitted to 3, a triplet. Why? Because I have told you about the n plus 1 rule, right? Told you about the n plus 1 rule. So here n is 2 in the case of HA, where the splitting is because of HB protons. So HB having the 2 protons, so 2 plus 1 is 3. So that is why this is giving you a triplet in 1H NMR, this methyl group. So now coming to HB, now how many peaks will it will give me? How many spirited peaks will it
Six.
give?
Six.
6. Okay. So here the scenario is that it will get split because of this HA as well as HC proton. So if HA will split it, then how many peaks are there? A quartet you will see, right? Because there are 3 protons, n value become 3 and 3 plus 1 is 4. So that is why you will see a quartet because of this methyl group. Now there is also HC proton that is present at the adjacent position. So now it is further getting splitted into another peaks because of this HC proton. So now this is also giving you a what? Triplet. So quartet plus triplet is the multiplicity for this CH2, for this HB. So now there is a rule that if you have this 4 plus 3, then how many peaks you will see in the NHNMR? 6. Not the 7, but 6 peaks are visible in 1HNMR. So whatever the multiplicity will come from HA and HC, if it is 7, then you will see one lesser peak in the 1HNMR. So here you will see 6 splitting for this particular HP proton. Is it right? Is it correct?
Yes.
Yeah. So now coming to Hc proton, that is CH2. Now for CH2, that is the Hc proton, Hb will split this up. Hb will split this up into a triplet again, right? So this is also showing you a triplet. This is showing you a sextet, and this is showing you a triplet. So now how many peak splittings are there? Just count.
12.
12.
12.
Yeah. So total 12 because 3 plus 6 plus 3. So you will get total 12 peak splitting in this particular compound in the 1HNMR. So Is it clear to all of you? Any doubt, any questions in this particular question?
Ma'am, they asked about secondary protons. So
Secondary protons.
yeah, so beta we have to consider or all.
All you have to consider, all are secondary. No? See, these are connected to two other things. In turn, this is connecting to two other things, right? Only you can say yes, this is the gamma you can consider or not. There is a question there, but CH2s are there, so you have to consider these much already, right? So if you consider this, then how many protons are there?
9.
Nine. So which is not present in the question. So you have to consider all the 12 splitting patterns. Okay. So sometimes you have to answer according to the question availability also. Okay. So is it clear?
Yes, ma'am. Clear.
Okay. So if it is clear, then coming to there is a splitting summary as well which I have given. So go through it also. This is a multiplicity pattern. So here if HA are proton present, then they will split up into the doublet because of this. Now if HA has to be concerned, then HB is equal to 2, right? So there is the identical proton HB. That is why they simultaneously split up this HA together. So here you will get a triplet rather than a doublet. Okay. So there is some multiplicity pattern which you observe in different case. So just go through this table as well. So now coming to problem number 13. It is also a simple problem. So they are asking which of the following has more chemical shift. Is it option A, methyl fluoride? Is
Yes.
Let me read out now. Okay. Is it the option A, B, C, or D? So now the chemical shift value depends on the electronegativity also. So here they are asking which is have more chemical shift, which means which is more de-shielded, right? So now you have to answer according to that. So now tell me which is the more electronegative atom, most electronegative, that is the fluorine atom, right? So it is the most electronegative atom. So it will take up the electron density from this carbon of very much, right? So making this hydrogens very much electron deficient, right? Because of the electronegativity of fluorine, it will take up protons, it will take up electron density from the adjacent carbon, and that is why they make this particular hydrogen much more electron deficient. That is why it will go to more downshield rather than upfield. So here the chemical shift value will increase for those protons which are electron deficient in nature. So if you are going to option number D, iodide is not that much electronegative. So that is why your hydrogen is not that much electron deficient. So here the electronegativity trends play an important role to identify which chemical shift of the proton is present. So here, due to the electronegativity which is higher for fluorine, you will get a chemical shift value for this particular proton as 4.26. So here it is going that much de-shielded, then chlorine, then bromine, and then iodide. So the chemical shift value for iodide is very much less because it is less electron. It is actually very less electronegative atom. Okay. So the correct option will be option number. So here you will get option number A as the correct answer, right? Because of the higher electronegativity of the fluorine atom. So is it clear?
Yes.
Yeah. So if it is clear that why the hydrogens are going downfield because of the electron deficient nature, so this is a very important concept in the 1HNMR field. So you will see that yes, electron negativity is playing a very much efficient role in the chemical shift values. So coming to problem number 14. So guys, this is the last problem for this session, and we will be meeting in the next session on Friday 6 to 8. So this is the last problem for the session. So the problem number 14 is saying that aniline does not undergo Friedel-Crafts reactions using AlCl3 because
Acid base reaction.
yeah, acid base reactions are there. So this class is very much straightforward because this is the week 1. So I am just going to increase the level for these questions in the next class, because guys, today this is a very first class and the basic has to get clear in the first go. So that is why I'm just adding up your confidence or adding up your morale so that you can get a better idea of the things. Okay, so here the aniline is not going to react in the Friedel-Crafts reaction in the aluminum chloride, because the option number A is aniline is deactivated due to the minus R effect of amine. Aniline reacts with AlCl3 to form a Lewis acid base adduct, both A and B, or none of the above. So here the option number A, just think about aniline and just think aniline is getting deactivated due to the minus R effect of amine group. Is aniline having the minus R effect or the plus R effect? Can anyone tell me? Aniline having the
Plus R.
plus R, right? So because the nitrogen is having the lone pair of electrons, so it is having a plus R effect. So the option number A is getting eliminated, although because of the wrong statement of the minus R. So it is having a plus R effect. That is why this is getting eliminated. So now if it is getting eliminated, then this option is getting eliminated, and none of the above is not the correct option, because here aniline is getting reacted with aluminum chloride to form a Lewis acid base adduct. So guys, whenever you are treating aniline to the Friedel-Crafts reaction, then you have to then you don't have to take the aluminum chloride, because it will form a anilinium salt and to get this particular compound, and your reaction will never go forward. So your reaction is not going to happen if you are adding alanine in the normal Friedel-Crafts alkylation or acylation conditions, which is requiring the aluminum trichloride. Okay. So this is the correct answer, that aniline is forming a Lewis acid base adduct with aluminum chloride. So is it clear to all of you the question?
Yes.
Okay, so if it is clear, then I am just wrapping up for today. So this is it for for today. So I hope you guys have just understand all the questions. If you have any query, anything regarding the whole lecture, then just let me know. You can comment on the YouTube channel, or it's better to just ask me in the next session, so that we all of the people will know what is the query and what is the answer. Okay. So thank you so much for joining the session. So now,
Ma'am,
yeah,
the assignments which we are getting, are they from the lectures or different?
actually,
Because the first week assignment was out of the lectures. Like
out of
it wasn't from the lectures.
okay. What
Those
was
10 questions,
yeah?
yeah,
So the content of the assignment questions was
was not from the lectures.
not from the
Like
lecture.
it was,
So
yeah,
what you have taught for the lecture? The content I'm asking.
NMR and electrophilic aromatic
Yeah,
substitution.
for the lecture you have taught that. Okay. So assignment is from.
Yeah. It is from various different topics as well.
Okay, actually, the assignments are solely dependent on the course instructor. So what they have given you, that is the only assignment, because I have to told that take the tutorials, and I'm taking the tutorials only. So the tutorials is not based on the particular assignment. So I'm actually not going. I have not gone through the particular assignment, so I don't know what they have included in that particular assignment, right? So
Okay.
yeah.
Actually, I had a couple of doubts in those 10 questions. So I thought ki maybe this lecture is based on those assignments.
Okay, okay. So
Hmm.
actually, we have not interacted with the course instructors. So according to the week schedule, we will be taking the lectures.
Okay, okay,
Yeah. So if you have any query now, just ask them in the next session. Okay.
okay,
Actually, first
okay. Thank you.
assignment with 18 questions. Am I right? Or 10 questions?
Sorry.
First assignment with 18 questions. So,
Okay.
is this right or?
See, I'm telling now. I don't know about the assignment. I haven't looked at it. because the course instructors are those people which are setting up the question, which are taking care of the questions. I'm nothing have to do it with it, right? So I'm just taking up the tutorials, not the assignments. Okay.
Okay. Thank you.
Okay. So thank you so much for joining. So I'm closing the session now. Thank you.